In this short video, we're going to be looking at the content in the Jupyter notebook called 2.1 Basic Optimization Demos. I'm going to open up a live version that you can follow along with by clicking here in the README of the repository to open up a live instance of the repo. If you do that, you'll get a tab that looks like this that shows you a list of all the current Jupyter notebooks and other content in the repo. And then again, we're going to look at this one right here, 2.1 Basic Optimization Demos. And here it is. This notebook accompanies Chapter 2 of the text that you can download for free on the book website, mlrefine.com. In that chapter, we introduce mathematical optimization and two core algorithms in machine learning, gradient descent and Newton's method. So the interactive demonstrations here illustrate those two core algorithms. Those two core algorithms are applied to everything from linear regression and logistic regression to support vector machines to neural networks to kernelized models, the whole shebang basically. Before walking through the demonstrations in this notebook, let me point you to the resource where you can find more technical details about the concepts themselves. That is Chapter 2 of the text. You can find that and download it for free by visiting our webpage, mlrefine.com, clicking on the tag here that says Download Chapters. It's Chapter 2 here, Fundamentals of Numerical Optimization. So I'll click on this link. Up will come a PDF of this chapter. Now let's scroll down to a figure that we're animating in the demonstrations in this notebook. Here it is. The concept being illustrated in the first two demos is that of gradient descent. This is one of the fundamental algorithms of machine learning, and the whole purpose of it is to minimize cost functions, like the one shown here. That is, we want to try to find the smallest point on this function. So how does it work at a high level? How does gradient descent work? We start at a point w0, some point on the cost function. Here it is. We'd make a linear approximation to that point on the function. Now you can read in the text that it's quite easy actually to find the downward direction on such a linear approximation. So we find that downward direction, we travel downward a certain distance, then we hop back onto the function. We repeat that process. We draw a linear approximation to the function, we compute the downward direction, we travel in that direction a certain length, and then we hop back onto the function and we repeat. If you do that enough times, you can get to a minimum of a cost function like the one shown here. Now back to the notebook. This is exactly what we're illustrating with the first two demonstrations. The first one is called gradient descent applied to a simple convex function with deceivingly difficult to hand compute minimum. Here it is algebraically. It's just a simple polynomial, but you can try to compute by hand its minimum. It's actually quite hard to do. Here it is plotted over a small range of its inputs. There's the minimum. Visually, it's somewhere between -2 and -1. If you go down to the next Python cell, this is the gradient descent loop to minimize that function, so we need to activate that cell. The next cell calls the gradient descent function and runs it a certain number of iterations, in particular 20. The final cell in this demonstration animates gradient descent exactly as that figure we just showed from Chapter 2. So we begin at a certain point, make a linear approximation, travel downward on that approximation, then we hop back onto the function and repeat. And repeat. Notice we've slowed down gradient descent quite a bit just so we can visualize what's going on in practice. Gradient descent works much, much faster than this. Also note that the points have been color-coded for visual representation from green near the beginning of the gradient descent run to red as the algorithm converges. Now let's go back up to this Python cell where we ran gradient descent. Notice there are several parameters here you can play with. You can change either the initial point of the run, which was at -2.7. Here you can see that down here in the graph. That's where we started. So you can change the initial location. You can change alpha, the step length. That controls how far we travel down each linear approximation. You can read more about that in Chapter 2. You can also change the maximum number of iterations that we run. You can change any one of those parameters and then rerun both this cell and the cell that animates gradient descent just to see how messing around with those parameters affects the behavior of the algorithm. Okay, let's go to the second demonstration. This shows you how gradient descent works on a prototypical non-convex function. Algebraically, that non-convex function is shown here and then plotted over a small range of its input by activating this Python cell. The next cell, we have the gradient descent function for this cost function. Notice the only thing that's changed here between this cell and the one for the convex cost function above is simply the calculation of the gradient or derivative shown here. Anyway, we need to activate this. Then we run gradient descent. Notice we have the exact same parameters we had before, the initial point W, alpha, and the maximum number of iterations, which you can play around with. Once we run that cell, we can animate gradient descent by activating this cell here. Again, right, we have, at least for the first couple of steps, showing you how the linear approximation is formed. You travel downward on that linear approximation, you hop back onto the function, and you repeat. That's how you go downward. Now with a non-convex function, in particular, you'll find that you might not always reach the minimum by running gradient descent. Okay? You can find examples of that in the text, or you can find examples of that yourself with this cost function simply by manipulating these parameters and rerunning to see how gradient descent runs when you change, say, the initial point or the step length or the maximum number of iterations. Okay, let's move on to demonstration 3. Demonstration 3 applies Newton's method to that convex function we saw in demo 1. It's shown here algebraically. Again, it's a simple polynomial. Let me show you where that concept is located in the textbook. It's in chapter 2, which we've already pulled up. Okay, here is the gradient descent demo. If you go down a few pages past additional information about gradient descent, you'll find the introduction to Newton's method. And in particular, these next two demonstrations illustrate Newton's method as shown in this figure, figure 2.11. In the same spirit as gradient descent, Newton's method works by taking approximations to a cost function in order to find its minimum. So let's start with the cost function on top in this figure. It's convex. If we begin at a point W0, as shown here, instead of taking a linear approximation as with gradient descent, we take a quadratic one. That's what Newton's method is all about. Here it's shown in blue. Then we travel to the minimum of that quadratic approximation and hop back onto the function. Notice we're going downhill, which is what we want. We repeat, we draw another quadratic approximation, travel to the minimum of that quadratic, and then hop back onto the function, going downward on the cost function in general. Computing the minimum of these quadratics is pretty easy to do. You can read technical details about how to do that in the text. It's the core part of Newton's method. Now, when you apply Newton's method to a non-convex function, sometimes you can get into trouble. Okay? If you begin at certain points, like W0 here, it works as with the convex function on top. That is, you take a quadratic approximation, you go to its minimum, you hop back on the function, and you're going downward on the cost function towards a minimum. But if you initialize at bad points on the function, like the concave point shown here, or the concave portion of the function shown here, then the quadratic approximation is no longer convex, no longer facing upwards. Like a cup, it's facing downwards. That means that you travel not to its minimum, but to its maximum. And in general means that you're climbing upwards on the cost function instead of going downwards. This is all illustrated in the demonstration in the notebook. Let's go back to that. So in demo 3, okay, we apply Newton's method to the convex cost function. So here in this cell is Newton's method. We need to activate it. Then, as with the previous demonstrations, we need to run it. Notice there are fewer parameters here for Newton's method. There's no longer a step length alpha. There's only an initial point W and a maximum number of iterations. In the next cell, we animate what was shown in that figure. That is, we run Newton's method. Here's our initial point. There's our quadratic approximation. We travel to its minimum, hop back onto the function, and repeat. This is shown for the first few steps, and again, points are colored from green to red as the algorithm converges. In the final demonstration, we'll apply Newton's method to minimize our non-convex function, the one we saw in demo 2. It's shown algebraically here. Let's activate the Newton's method Python cell and then run Newton's method. Notice again we have two parameters here. One is the initial the initial location, the initial point W, and maximum number of steps or iterations. So we need to run that Python cell. Finally, we animate the steps by running the final cell. We'll show you the quadratic approximation for the first few steps, and then things proceed. The color, and notice again, the color of the points is coded from green to red as the algorithm converges, and we've slowed down things a bit or slowed down Newton's method a ton just to be able to visualize what's going on. In practice, Newton's method works much faster than this. It's important that you play around with the parameters in this particular example for Newton's method because you can easily break it. You can easily break Newton's method, as illustrated in that figure from the text over here. Remember how if you initialize at a bad point on a non-convex cost function, you can actually climb hills with Newton's method. You can reproduce that behavior by simply changing the input, or the starting point for Newton's method in this cell and rerunning both this cell and then the animated cell. Well, thanks for watching. I hope you enjoyed this walkthrough, and I hope you'll play with this notebook yourself. You can find it again by traveling to our GitHub repository at github.com/jermwatt/mlrefined. You'll find that notebook here. It's 2.1 basic optimization demos, along with many other notebooks demonstrating concepts from the textbook. And remember, you can find more technical details about both gradient descent and Newton's method in Chapter 2 of the text that we were looking at previously. You can find that by going to our book website, mlrefined.com, and clicking on Download Chapters. It's right here, Chapter 2, Fundamentals of Numerical Optimization.